So, good morning, everyone, and welcome to a log analysis session for FlightCoach. I've got Andy here from New Zealand, and he and I have for ages worked together on the ArduPilot part of the FlightCoach system, and particularly on the sort of autonomous aerobatics, which we had a lot of fun with some time ago. But the reason for this video today is I'd noticed that there were some people struggling on the Flight Coach Facebook group with the getting poor, what we call state estimation, getting poor tracks in Flight Coach. And so what I wanted to do was grab a couple of those logs, and I've had two users who had issues that have very kindly given me a log each that is showing problems. And we'll have a look at those logs in FlightCoach, and then we'll dive into them with some of the ArduPilot log analysis tools, and we'll look at why the issues are happening and what you can do if you're facing these types of issues. There's also a new feature in ArduPilot that I wanted to point people to, which can make a very big difference to these types of issues. And so I just wanted to, in relation to these logs, explain that a little bit. So Andy, are we ready to start diving in?
Yeah, Trish, thank you. Sounds great.
All right, so I'm going to share my screen, and then Andy is particularly here to sort of keep me honest to make sure that I explain things properly. So what I'm going to do is, first of all, go to everyone's favorite web app, FlightCoach, and we'll pop into the plotter. And what we're going to do is, so I've got these couple of little log files, right? So these are log files, and one of them is from Philippe Serda, and the other one is from Stuart Shale. Thank you to both of those users for contributing their logs. And so we'll open up the first of those in FlightCoach. And so I'll pop into my users directory and then FlightCoach and then Philippe's log. And we'll just use the default location. Right, this one is really quite extraordinarily bad. Now, of course, it might be that Philippe is an extraordinarily capable freestyle pilot and is able to do some amazing maneuvers. I mean, this one where he manages to do a 90-degree turn and then flip across to the other side of the flying field instantaneously, that would have been impressive to see in the sky. But you can see clearly there is something going wrong here in terms of the estimation of the position. So ArduPilot's getting the position wrong. I mean, we can see up here, there's a little one, if we zoom in here, can you see it there? Where there's, again, a very impressive maneuver where, the plane suddenly reverses back up after taking a dive and then comes back down again. So let's have a bit of a look. So we'll look at this from the top as well. And yeah, so really very, very messy. Okay, so that's what it looks like in FlightCoach. And let's have a look at the other one as well. I'll just open the second one and the one from Stuart, which is a bit more subtle. So this is the one from Stuart. So this is from Pennsylvania, and this looks a bit more like you would expect, a log from a good pilot. But there are some oddities. So see this one down here, right, where there's that step jump down there. That one is particularly obvious. All right. So what we're aiming to do is to provide some explanations as to why these types of things happen. And then what we're going to do is see about what you can do about it, how you can change both the physical setup and the settings of ArduPilot. And So let's dive into it. So let's start with Stuart's one. So that's this one we've got on the screen at the moment. And I'm going to bring it up in a tool called Mav Explorer. Now, there's lots of different tools that ArduPilot can use. Another one that people like using is plot.ardupilot.org, which is great because you don't need to install anything. So you can open the log in a viewer. So I'll actually go and open one of these logs in the log viewer. And it actually has a little bit of a sort of a 3D viewer in it, which means you can see some of the same characteristics. It doesn't have the wonderful colorization that's done on FlightCoach, but you can see some of the sort of the properties. And there's various plotting and things in here. So I'm not going to be using this plotter. All of what we're going to be doing today, you can get the information out of this plotter, but I'm the author of this particular tool, and it has some built-in features in this tool that make some of the analysis easier. So what I'm going to start by doing is bring up a map. And so with the map, I'm going to bring up two plots on the same map. Now, Mav Explorer's main issue for FlightCoach and aerobatics is that it's a 2D map plotter, right? So this is a downward-looking view from above, which for most things with ArduPilot is fine, but obviously that doesn't capture the sort of the 3D-ness of aerobatics. But you can already see here that if this was a really good capture, if all of the state estimation in ArduPilot was happy, the green line and the red line here would overlap each other very closely, right? And to give you an idea, I'm pretty sure these grids are 10 meters apart. Yes, they are. They've just measured I clicked on 2 points and measured as 9.8 just because I didn't click exactly. They're 10 meters apart. So you can see that these two lines are around, 8 or 10 meters apart. I could measure that 7 meters apart at that point.
I'll
Andy?
interrupt you a bit here. I think it'd be really
Sure.
useful to explain the difference between the green and red lines and what
Mm.
they.
Right. So the GPS is the one marked GPS is this, which is the red line, is the raw readings that are coming from the GPS, right? So what ArduPilot is trying to do when it's getting a state estimate is it's trying to combine a whole lot of sensors. And the sensors on a typical flight controller, if I hold up, here's a flight controller, right? And I've got a GPS handy on my desk. I've got a drawer full of them behind me, but anyway, you know what a GPS looks like. So a flight controller, it's got the different sensors it's got. Typically you've got a GPS. You usually have a barometer, which measures pressure, right? And pressure can be used as a proxy for altitude. And then you have typically you have a compass, which gives you the magnetic field strength in 3 axes. So a compass isn't a 2-dimensional device, it's 3-dimensional. So it gives you the field strength in 3 dimensions, towards the front of the plane, towards the right of the plane, and towards, downwards out of the bottom of the plane. Then you have perhaps the most important sensor, an IMU, inertial measurement unit. And that one provides you with 6 numbers. 3 of them are accelerations. So it's the acceleration vector, accelerations, forward and, right and down. And the gyroscope, which gives you the rate of rotation in 3 axes. So the x-axis of the gyroscope tells you how rapidly it's rotating the flight controller. The y-axis is how rapidly it's pitching, and the z-axis is how much it's yawing. All right. So together you've got all of these different sensors, and some aircraft have airspeed sensors, or they have multiple GPS, multiple IMUs, multiple barometers, multiple compasses, LiDARs, all sorts of different sensors you can have on a complex vehicle. But most people running FlightCoach would have GPS, barometer, IMU, and maybe a compass. Okay. The problem is that all of these sensors are lying to the flight controller all the time, right? They're all giving incorrect readings. They're never exactly right. Or if it is, it's just coincidence briefly. So, and ArduPilot's job using something called an extended Kalman filter is to take all of the things that aren't quite right and try to discern the truth out of it to give the overall position. So back to your question, the GPS, this view is showing the latitude and longitude from the GPS. And you can see here, there's the little dots here. There's a little dot there. Not sure if it's clear on this view. Little dot, right? Each of those dots is a reading of latitude and longitude from the GPS. And typically they come in at 5 hertz, right? So every 200 milliseconds, we have a latitude, longitude reading. More rapidly, we're logging these little green dots, right? Which is the current best estimate of what the true position of the vehicle is, combining all the other sensors. And you could say, well, I just want to trust my GPS. And maybe by the end of this video, you will, think that's a good idea, maybe not. One of the things I'm going to be showing in this video is how you can tell ArduPilot to trust the GPS more, right? So, and to say, I know my other sensors are rubbish. I think I've got a great GPS. The guy who sold it to me said it was the best ever. So I want to trust the GPS more. And if you want to do that, you can. There's a setting for that. But let's keep diving in as to, why we're getting this discrepancy. Okay, so another way of looking at this is sort of a graphical way of looking at the horizontal position error, right? Or horizontal position. We can look at this as a graph number. I'm looking under EKF3 here, innovations, position innovation northeast. Now, an innovation in the language of a Kalman filter is a difference between an observation and a prediction. So at each point in time, ArduPilot's EKF is predicting what's going to happen next, right? Because it knows roughly the laws of physics. It knows that if you're here and you're moving in that direction, then a couple of milliseconds later, you're likely to end up there, right? Moved a little bit in the direction that you were going. And the same within the rotations and everything else and all the accelerations. So ArduPilot, with all of its sensors, is able to predict the future. And this graph here is the difference, these IPN and IPE, that's the innovation position north and innovation position east, which is the difference between the prediction and the observation from the GPS. So the GPS is giving us our latitude, longitude estimates. And I say estimates because a GPS is itself an estimation system. GPSs are magic devices. They're little miracles, really. But they are, there's these amazing flying clocks in the sky, the satellites, and the GPS is pulling these incredibly GPS receiver, or GNSS receiver, really, is pulling these amazingly weak signals out of the sky, and then it's doing a least squares estimate of the position, taking into account relativistic effects. And I always think that's very cool, the fact that you do have to take into account, the special theory of relativity in order to get your position with a GPS. I implemented a GPS once many years ago, and at first I left out the relativistic corrections and always got quite a poor position. And then once I added in the relativistic stuff, it was a lot better. So I thought that was very cool, the fact that relativity matters for GPS positions. Anyway, so what we can see here is that there's quite a few locations where these quite significant discrepancies between the estimated easterly position and northern position and the so if we zoom in here, and these two little things are actually this one of the tricks that Mav Explorer has is it synchronizes the graph and the map. So if we zoom out on the map and we go back to all of it, that's our whole flight. But if we zoom in onto this bit that seems to have particularly large numbers, right, we can see here that the place where it was particularly high innovations was this little maneuver here, right? And that's where we were getting that 7 meters or so discrepancy. Okay. So what causes this? Well, you get these discrepancies when there are inconsistencies between the sensors. So the reading from the magnetometer, your compass, is not consistent with the readings from your IMU and your barometer and your GPS. And ArduPilot is effectively weighting the different ones. It's not really just a weighting. It's more complex than that, but effectively weighting the different sensors to try to come up with the truth. And now, the sensors themselves, some of them actually provide their own estimated accuracy. We can have a look at that for the GPS, right? So we can bring up this little graph called GPS accuracy. And it's definitely worth having a look at. So, by the way, in a really good flight, if everything was set up perfectly on the aircraft, you would expect these innovations to be maybe, half a meter, a quarter of a meter or less, really quite small. And you would expect that these tracks, the green and red line, would be within, a very small margin of each other. So this graph here gives us the first little bit of an insight into what might be happening. Let's first of all concentrate on this yellow line, which is how many satellites it's able to see. And we can see that it's starting towards the beginning of the flight, mostly having sort of 8 or 9 satellites, right? It's on this right-hand scale here, and occasionally dropping down to 7 satellites down here. Now, that's by modern standards. Back when I started with ArduPilot, getting 9 satellites, that was good. But these days, I would not take off if I had less than 25. And the modern GPSs can lock onto a lot more signals. When it says number of satellites, by the way, that can be a bit misleading because it might actually be getting multiple signals from a single satellite. Probably not with the particular GPS in this aircraft, and we can look that up.
Dredge, I don't want to sidetrack too much, but I wonder, a question on people's minds will be, what sort of GPS hardware is good to use?
So this particular one, so that's what I've just looked at here. This is messages blocks. I'm looking for the string BLO, and it's finding this U blocks string, right, which gives us the hardware version and also the firmware version on the GPS on this aircraft. And this little capital A here is the key. That means it's a U-Blocks M10. A is hexadecimal for 10, right? So that's an M10. And the M10s are very popular. They're relatively cheap GPS modules. They're single frequency, so they only do the L1 frequency. So they're cheap and cheerful. Unfortunately, the M10 has this problem that it takes a long time to get a decent lock. And what we're basically seeing is some of these changes are because, Stuart was flying upside down for part of the thing, which is all part of the fun and games in aerobatics, which means the sensor, the GPS, was probably pointing at the ground, unless he's got it mounted in an unusual fashion. And of course, the satellites are up in the sky, which means he's not getting very good signal onto the GPS for some of the flight. But you can see there's a general trend of increasing number of satellites towards the end of the flight. So, and I'm guessing it wasn't that all of this was inverted and all of this was right way up. That would be highly unusual as a maneuver. So what's happening is the classic U-Blocks M10, which is that it takes an amazingly long time to get a decent lock, right? And you have to wait. Quite often people report that, that they get a much better result later in the day. even after they've changed battery, because it tends to have a little, it holds some of the information it needs even after you power cycle it with a new battery. So, your second flight might be better than your first. So one of the tricks, if you've got an M10, in fact, for most GPSs, is turn on your plane early and let it sit there for a while, because the results will be better towards the end of the flight than towards the start of the flight. Okay. Now, if you've got the money and you can get yourself a dual frequency GPS, you'll do even better. And what I mean is one that can do, say, L1 and L2, or possibly L1, L5, although with the L5 frequency. So these are the frequencies that the satellites transmit at, right? And each of those frequencies has different modulations and properties and things. But if you've got two frequencies that you transmit on, or that you can receive on, then you can get a much better fix than the single frequency ones. And so I've got a whole bunch. I've got a drawer full of GPSs here. This is my GPS drawer, right? And so the sort that I was using when I was doing aerobatics, I haven't been doing much aerobatics lately, but I was using what's called an F9P. So this is an example of an F9P, and it's pretty chunky. This is another. That's another F9P. There's also route. They come in all different form factors. There's one there. You'll notice that is quite a chunky GPS, right? And because it's got a huge antenna in it, it's relatively heavy. It's a lot bigger and chunkier, right? But it's also dual frequency, and it will give vastly better results. Now, you can get small versions of the F9P. This is a small F9P, right? But again, you're going to be paying a lot more for a GPS like this than you would for the M10. I'll see. Yeah, here's an M10. So this one here is the same as what it's different physically. It looks different physically, but it's the same sensor underneath as what Stuart had in his aircraft. And you can get even smaller, cheaper ones. There's a tiny little one, and so there's you certainly can get better GPSs than what Stuart has, but the M10 is popular because it's relatively cheap. And if you leave it for long enough before takeoff, it can get a reasonable lock. But let's look again at these numbers. So the yellow number is how many satellites. Then we've got the red, green, and blue numbers. Now, these are the self-reported accuracies. In other words, these are the GPS itself telling the flight controller how much the flight controller should trust the numbers from the GPS, right? So because the GPS itself is an estimator, it actually has a little physics model built into the GPS. And one of the problems is that the u-blox physics model is limited to 4 Gs of acceleration. Now, some of the pilots will be doing more than 4G maneuvers. And if they're pulling more than 4 Gs, the GPS cannot physically track it, right? Because it is limited to a maximum of 4G. Beyond that, there will be errors no matter how good a u-blox you have. Though ArduPilot's IMU integration and all the other sensors and compasses, etc., can make up for that, right, to quite a large degree. But yeah, you will get errors. Now, most of the time, we can have a look at the accelerations that that Stuart had in his flight. Let's go and have a look at the accelerometers and see what sort of maneuvers he was pulling. So this is in meters per second, and really what matters is the yellow line, which is the overall length of the acceleration vector. And you can see up here, he was pulling 53 meters per second, 5.3 G. So there was no way the GPS was going to keep up at that point in the flight, right? And here, 5.1 G there, 4.6. Even these maneuvers here, 3.2 G. He's really pulling some Gs. If you were on board that aircraft as a little micro human and feeling that, you'd feel it. So that's the first thing. So know your limitations of your GPS and know that, it's never going to be perfectly accurate. Okay. So what do these red, green, and blue numbers mean? So the red number is the horizontal accuracy. So that is the GPS's own estimate of its accuracy in meters, right? It's like the one standard deviation approximately, expected error. So it's saying that here's my position plus or minus 6 meters, right? Because I'm reading there 5.3 meters at that point where I have my cursor. So when I move the cursor, there's a number that appears down here. And so that's about 5.3 meters of horizontal accuracy. Now, U-blocks is notoriously optimistic in their accuracy estimates. So when they say that there's an error of 5.3 meters, the rule of thumb is double or triple that for the actual range of errors that it's going to be getting, right? The better quality U-bloxes are a bit more realistic, but these cheap and cheerful ones are highly optimistic. Okay, so then we've got the blue is the vertical accuracy. That's how much error there is in height, which means in this case, we've got 5.2 meters of horizontal error plus 5.1 meters of vertical error, right? That's already getting to be a fair bit. That's enough that it makes a difference in your score. And then there's the speed accuracy is the green. So this is the estimate of the speed. And that's really important because the speed accuracy is very important for predicting what's coming next. All right. So when these numbers are large, it means that the GPS is telling the flight controller, really, I don't really know what's going on, but here's an estimated latitude and longitude where I think I might be. And then, good luck to you. All right. So what would good numbers be? With a really good GPS, you would hope that the numbers are down below a half meter coming out there, right? And in fact, the top-notch ones, particularly flying straight and level, more like around 5 to 10 centimeters of error here, of estimated error, right? So quite different order of magnitude, but you'll pay quite a lot of money for a GPS that'll get you that. So they're not cheap. Okay, so that's our raw GPS. Now, then we can have a look at some of the other sensors. So the other main sensors, we've got our IMU, we've got our barometer, we've got our magnetometer. Which one do you want to dive into next, Andy?
Oh, look, probably the IMU, I guess.
The IMU. All right, so let's have a look at what's happening in the IMU. Now, one of the things we often look at in the IMU is there's the vibration and the clipping. So let's look at vibration. Just how badly is this plane vibrating, right? And it's vibrating a fair bit. These are basically low-pass filters, giving like a average amplitude in a band of frequencies that are interesting for vibrations. And you can see we've got some peaks up here of like 44 meters per second. That's like that's quite a lot. This one a little bit less, and average down here, this is not too bad. So look, for a plane that probably doesn't have a lot of effort put into vibration isolation, this is actually pretty good. So one of the good things that people have in the world of FlightCoach is they're not trying to get ArduPilot to control the aircraft, which means you can actually do quite a bit in terms of vibration isolation of the flight controller and not cause control issues. If you put too soft vibration isolation when you're trying to get ArduPilot to fly the vehicle, what's happening is ArduPilot's flying the flight controller, but the vehicle is moving differently from the flight controller, right? So if it's too soft, you get this sort of jelly effect, and you end up not flying the vehicle very well. But that is much less of an issue when all you're trying to do is track or a ribbon in the sky for FlightCoach. So you can put
True.
a fair bit of isolation.
What, what sort of mounting would you recommend just offhand for a light flight control that would typically be
So
used for flight coach?
the main thing you need to look at, this vibration, it's not low vibration, but let's see whether there's any actual clipping, which what really matters. So let's go and have a look at that. So sensors, accelerometer, clipping. So clipping is when you are going beyond the capabilities of the IMU. And that's not an issue in this flight. There's only 2 clipping events here, right at the end of the flight. I bet that's when he's touching down, hitting the runway, right? And briefly clips, basically gets a sample from the IMU, which is beyond the limits of what the IMU can actually measure, okay? Which might be, say, 16G or 24G, depending on the type of IMU. We could look up what IMU it is. This particular IMU it's an MPU 6000, and we can also look at what type of, it's an Omnibus F4 Pro flight controller, right? And running ArduPilot 453, and it's an MPU 6000. Now, an MPU 6000 is an ancient IMU. It's not a bad IMU, but it's quite ancient. It can't do something called fast sampling. It's slow sampling. And it means it can't necessarily see all the clipping events, because the clipping events could be hidden inside the speed of the sampling. But just based on this graph, the IMU is coping with the vibration. So yes, Stuart could put a little bit more, bring this down a little bit. I suspect it wouldn't make a lot of difference, because the IMU isn't his problem, probably. But we'll need to look a bit more in some of the other things. People focus often a bit too much, particularly if they've got a more modern IMU that can sample much more rapidly. So the MPU 6000 is only sampling at 1 kilohertz. More modern IMUs be sampling at several kilohertz, and the faster it can sample, the less issues you get with aliasing effects and other things. So, all right. So let's move the IMUs off and say that in my sort of brief look at this log, I don't think the IMU is his issue. All right, so let's have a look at some of the other sensors. Which one next? We've got Baro and Compass.
Well, let's look at the compass next, shall we?
At the compass. Okay. So the way I typically look at the compass, and this is one of the advantages of using this particular tool, is it can run a graph like this. Now, this looks like a mass of wavy lines that, only a sort of a state estimation person would like, but it does actually have some sanity to it. I'll just zoom into a little bit of it, and then towards the start of the flight. So what this has got, a compass gives 3 readings. It gives the magnetic field in the x-axis, which is along the front of the plane. It gives the magnetic field on the y-axis, which is going out the right-hand side of the plane, and it gives the magnetic field in the z-axis, which is going out the bottom of the plane, right? And then what we've got is 3 more lines, which is the expected magnetic field. Now, where do we get that expected magnetic field? Well, it turns out that there are some amazing geoscientists in the world who have built really sophisticated models of the Earth's magnetic field, right? And it really is an incredible science that they've managed to do this to massive accuracy. So we've leveraged that, and we have built into ArduPilot as big tables, and built into this tool, we have tables that tell us what the expected field is at any point on the Earth's surface. And then what we've got is we know what we think we know what the orientation of the aircraft is, right? And so if we know the orientation of the aircraft and we know where it is on the Earth's surface, we can predict what the magnetic field that it should have seen is. And those two numbers should, if this was a really good compass, really good setup, they should line up with each other. And you can see they sort of generally do, like the red line and the green line, which is the x-axis, you can sort of see they're correlated with each other. They've got the same little bumps, but there's quite a significant gap here. If we measure that gap, so that's a minus 241 milligauss, and that's a minus 122, so about 122 milligauss. So how significant is that? Well, roughly speaking, the Earth's magnetic field, the strength of the Earth's magnetic field varies all over the planet, but good rule of thumb is sort of 300 to 400-ish. So that means that's about a third of the Earth's magnetic field. Now we can see that the y-axis, there's some difference, the blue and the yellow here, there's some differences, and the z-axis, there's even bigger differences. And if we have a look at later parts of the flight, we will see some where it's even more dramatic, right? Where, the expected Z field down here was about 500 milligauss, and what we're actually seeing is, 860. You'll also notice that the peaks and troughs don't quite line up, right, with the with each other. So it's not just an offset. There's something else going on, and that could be, for example, a bit of a misalignment. The compass is not quite pointing forward in the right direction. A little bit of tilt error, that sort of thing. So these differences are really good compass. These lines would be lining up with each other within maybe 30 milligauss or so, but instead we're seeing hundreds of milligauss error. So that means that, and let's have a look. The most common problem with compasses in aircraft like these is that current from the motor. There's motor wires and there's, current going into the motor, going into the ESC, and that current will generate a magnetic field. And the biggest problem is that magnetic interference from that current distorting the magnetic field. So let's have a look at the takeoff, right? If I put GPS.speed as yet another line on this very already complex graph, so now what I've got is this grayish line, terrible color scheme, and we can have a look at, during the start of the flight, as you can see the speed increasing, are we seeing a distinctive change in the magnetic field, how well it's aligned as we increase speed, which he must have been putting some throttle on here, right? And we're not actually. It's as we increase speed, there must have been significant throttle. It might be a bit here, but you'd expect that there to be a whole lot of current right at the beginning, because typically you put quite a lot of throttle to get off the ground. And this one, I'm not seeing a huge correlation between this acceleration as the throttle's pushed up and the amount of error in this magnetic field. Now, the other log, I've had a sneak preview of the other log that we've got here that we're going to be looking at later, and it's a completely different kettle of fish, right? That one, as you push up, as the throttle goes up, we're actually getting a really dramatic amount of magnetic error. So a different problem. All right, but in this one, what this means is on Stuart's log here, what he's got is it could be a bit of misalignment on the compass, could be poor calibration on the compass. He might need to redo his calibration. Or there could be that there's some other, a common thing is things like hatch magnets being too close. The flight controller is shifted relative to something like a hatch magnet. I've seen cases where people, they originally calibrated without a hatch magnet, then they put back in a hatch magnet because the hatch kept coming off, and then they find that, they get terrible results. So certainly this compass, it will be helping a bit in getting the estimate, but it not a lot because there's such significant error here, right? Now, one of the things we can do is we do actually have a tool where we could recalibrate Stuart's compass for him using the flight log, right? So what I could do is zoom back to the whole flight log. And now this is a very slow tool. So what I'm going to do is I'm going to do a reduction in the number of points. I'm only going to sample every fourth point, and I'm going to run an estimator where what it's going to do is, that was rather quick. It's a very small log, so I might rerun it with the full one.
Tridge, could I just interrupt for a
Yep.
second? I think something that people would be interested to hear is about the importance of calibrating the flight control in the model that you're going to be
Yeah, that's right.
flying.
That's right. Now, calibrating your IMU can be done outside. The acceleration can be done outside of the model. In fact, it's often best to be done that way on a bench, nice flat surface, right? But yeah, the compass absolutely has to be calibrated when it's inside the model. And you also have to be careful that the model is well away, not inside a house. Some people do it in their studies because it's cold outside, right? You've got to be well away from buildings, well away from metal in the ground, all these sorts of things. But what you can do is you can actually take a flight log and do the calibration. So that's what I've done for Stuart's one here. And this top graph is the original data where there's this sort of error, right? And then this is after it's been corrected. And we can see this bottom graph is saying how much of a difference it's made. And there's two different mathematical ways of saying how much difference it made. But if we look at the vertical scale here, this is in degrees. We can see that by one measure, this changed the estimated yaw by 73 degrees. Well, that matters, if you're that way versus 73 degrees around, that's a really significant difference in your yaw. And so this recalibration, right, these would be the new values that Stuart could use. Now, it can also do all sorts of other things. It can do scale factor estimation, elliptical estimations, and all sorts of things. You can dive into this sort of thing a lot. There's also an online tool. If you don't want to download and install Mav Explorer, you can use this. This is new since when I last was getting involved in FlightCoach. So firmware.ardupilot.org/tools/web-tools, this one. And there is a MagFit tool here, which uses a different mathematical approach, but it can produce some quite good results. And so what it's doing is it's also doing all these sort of estimation techniques, right? And it's saying that the current error is on average 383 milligauss. After fixes, it comes with 163 milligauss, which is an improvement, but still not brilliant. And it gives you the new values, right? These are, you put in compass offset X, he wants -328, Y -327, Z 261. Don't bother about the decimals. It really doesn't matter. You can also get it just to save those new parameters. You click save, and so you'll end up with a file, magfit.parm, right, which is this, and you can then just load that, and these are your new parameters you could load. So if your compass is causing you problems, the first thing is to make sure it doesn't have significant is correctly aligned, and correct orientation is very important. Some of the compasses actually they have an arrow pointing one way, but the actual correct orientation is different. The Holybro ones are notorious for that. And then make sure you don't have too much current interference from the motor. And then, do a flight. And if it looks like your compass doesn't look good, you can use this tool to get you a new estimate of your calibration, which will improve things. So worth doing. All right, so we've had a bit of a look at the compass, and certainly a compass, you can actually fly without a compass and it will work, but a well-calibrated compass will make ArduPilot state estimates significantly more robust. It will be able to handle those high G maneuvers better. It will have, less error. So it is worth having a good compass, but a bad compass is just a liability. You're actually better off not having a compass at all. So if you can't get a decent compass, you're better off turning it off. Okay. Although you might get a strange thing because if you don't have a compass at all, it has no idea which way you're facing until you start moving. And you'll find that in your FlightCoach ribbon, it'll do weird things right at the beginning as you're taking off, right? As it has no idea which way is north. Okay, so that's our compass. The final sensor that tends to be important is our barometer, right? And if I graph the baro alt and the GPS altitude, right? So now what I'll need to do is know what the height of the ground is around where Stuart's flying, right? Now I can do that by, seeing where the middle of the flying field is, which is over sort of here somewhere. And you can see if I move my cursor that there's a number 160 up here. It's about here. So it looks like he's about 160 meters above sea level. So what I'm going to do is graph baro alt and GPS. I'll say the first GPS, because you can have more than one GPS, which can be worth doing. Two cheap GPSs can be better than, and you might even orient one with the antenna up and the other antenna down. That's a possibility. So GPS alt minus 160. Okay. So these are our two altitude estimates. And you can tell ArduPilot, there's parameters in ArduPilot as to whether to use the barometer. Now, Stuart has chosen not to use the barometer. You'll notice that all of these EK3 source settings are GPS, 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 and compass for yaw, right? So in particular, POS Z, this is so vertical position. Stuart has said, trust the GPS. And that can be good and bad. The problem is that GPSs, due to the geometry of the way that the satellites are, the vertical is the worst axis for a GPS. And I should show you, there's a little round up GPS ArduPilot. I wrote an article some years ago called Big GPS Roundup, where if I can finally bring it up, here it is. So if you search for Big GPS Roundup, you'll find my article. And I did a sort of a deep dive into GPS accuracy. And so I had this little table, in this nice little location out. It was a beautiful spring day, and I had lots and lots of GPSs on this table, and I was doing lots of long-term measurements on their accuracy. Well, and it included the GPS. Did I have an M10? Didn't have an M10, although these M8s are somewhat similar. So you can sort of see these are these accuracy numbers. You really have to read the article to get all the details. But this was the test in my backyard, and then I did the test outdoors. So this is the outdoor test. And although probably because you've spent so much time upside down when you're flying aerobatics, the backyard test might be more representative. And what you see is that a lot of these cheaper GPSs, this number, the HEP number, that's the height error probable 50%. What this means, this number here, 3.76, says that 50% of the time there was a height error of more than 3.76 meters. Sorry, 50, yeah. So then there's this number here, which is sort of the 99 percentile. So, what this is telling us is that just occasionally we got errors of nearly 15 meters vertically, right? Rarely, but just occasionally. But, you know, half the time the errors were 3.76 or so, quite significant height errors. If you look at the more expensive GPSs, significantly less error. And if you really want to be fancy, you use something called RTK. We have an RTK base station. And then you get down to like 1 centimeter of errors, right? But you're starting to pay a fair bit of money to do that. All right, so that's an article that some of the FlightCoach users might find useful. So just search for big GPS roundup to get those details. Okay, so let's have a look at the barometric altitude versus the GPS altitude. And if we throw into this graph, then one of the effects you can get, GPS 0.speed, one of the effects you can get is that, in fact, I'd want the total speed, which is really what I want is the square root of GPS. This is horizontal speed plus GPS 0 vertical speed squared. So that's then the vector length of the speed. So it's rough estimate of like the airspeed, right? Speed through it's not accounting for wind. Okay. You can get an effect that at higher speeds, the baro becomes inaccurate, right? But it does have the advantage that the baro works when you're upside down, because it's not having to see satellites. But we can see that the discrepancies here, they're not huge. The worst case one we were getting about, so this is a value of like 69 and this is a value of 86. So like 17 meters difference between the barometric based measure and the geometric one from the GPS. Which one is correct is a little bit hard to say, but certainly when the GPS is upside down, it's quite likely it would have some significant error. But you get these airflow errors. And the reason why many people like Stuart turn off the baro is because you can get some airflow through the fuselage that changes the pressure, that changes the reading, and that can make quite a significant difference. All right. So he's not using the baro, so we won't focus too much on the baro. Okay, so let's try and cut to the crunch of, what can Stuart do to fix these particular issues? And let's have a look at pos dot rel origin alt, okay, something like that. And we can look and see whether these sort of steps. So this type of thing here, right, is what Stuart was seeing, which is why he asked about it. These sudden jumps, right? And the reason this happens is that the EKF, we had those sort of innovation graphs at the beginning, these position innovations, and let's have a look at the vertical position innovations. So position innovation down. And what we see here is that it was developing quite a significant vertical position innovation of like 4 or 5 meters. And we can look at another graph which will give us an idea as to whether the EKF was actually rejecting the GPS's estimate of position. And it wasn't, but there was this sudden correction. Let's have a look at this. We'll look at the just pos.alt, which is height above sea level, and gps.alt. And right, we can see that the GPS was smooth, right? And the reason the GPS is smooth usually is because it's actually filtered inside the GPS. So the GPS will trying to produce a smooth track. And the red line, ArduPilot, is trying to produce an accurate track. Now, a smooth track and an accurate track isn't the same thing, because ArduPilot is designed for flying aircraft, not monitoring aircraft. And it's a different task. When you're trying to fly the aircraft, you really, if you're coming in for a landing, getting a smooth ribbon in FlightCoach isn't the thing. It's not landing 3 meters underground is the thing, right? Because that tends to lead to a big crunch and, rebuilding efforts and lots of glue and tape and, that sort of thing. So ArduPilot, when it's monitoring, it's got this EKF statistical filter, and it will occasionally say, I've been trusting this sensor for now, but now it looks like, based on the current probabilities, it really looks like I was going down the wrong track, and it will actually jump the position, right? And that is what happened in the ribbon. So it's taken us an hour, but we've eventually got to the point where we're trying to answer the question, why this happens, right? And that's it. That's basically ArduPilot thinking that it's right, even though the GPS was doing a track up smoothly here. Then ArduPilot was saying, that's not right. That's not, all my other sensors are telling me that I'm actually going down here. The IMU and the compass, etc., was saying I was going down here. And then eventually the EKF said, well, no, I think actually maybe the GPS was right, right? And it comes back and jumps back. Okay. So one of the main reasons I wanted to do this call was we have a new option, this parameter called EK3 glitch rad. Right. So that is the radius around the aircraft's position that the EKF is willing to accept diversion from the GPS. So it's willing to accept up to 25 meters of error, and it will cruise on with its own estimate and basically say, okay, the GPS could be off by up to 25 meters. Now, if Stuart changed that to 0, then that would tell ArduPilot that it's got a special case for 0, where it would tell ArduPilot that, okay, lock in, trust the GPS, right? Lock into that, and you will end up with a much smoother track. If we look at the help for that parameter, param help, and or you could search for this EK3 glitch rat on your, with your favorite web search tool, and you'll find the explanation of it. All right. And this parameter was originally added for people doing aerobatic multicopters, racing, the little racing quads, right? That's why it's described in here. So we don't have a special page for this for the aerobatic planes, but it's very similar concept, right? Similar sort of G-forces people get. And there is this explanation in here. But you should read through this, right? So read through this help, and the help will show on the ground station like Mission Planner when you look at the parameter. But there's a special to value of 0 that changes the way the EKF deals with GPS. And you will end up with much smoother tracks. Much less likely, it could still happen. There are still some circumstances where there are jumps, right? But much, much fewer. So this track almost certainly would have been smooth, and Stuart probably never would have, asked the question. But is it more accurate? And that's the question, right? Because smooth and accurate isn't necessarily the same thing, because of all of the things I said earlier. The GPS was struggling, particularly towards the start of the flight, where it hadn't managed to lock on to many satellites. Particularly as it's it's a relatively low-end GPS, it's upside down for a lot of the time. So it will be smooth, but it won't necessarily reflect what the aircraft actually did. But many people would perhaps prefer that, right? And might actually, I just had a weird thought. We could actually take these sort of consistency errors and error estimates in the scoring, I guess, in some way. I'm not quite sure how you do that, but anyway, crazy idea. So it's worth, if you've fixed up everything the best you can. So fixing the compass, definitely worthwhile, making that a lot better. Maybe a little bit more isolation on the IMU, but as I said, it probably won't make much difference. Then it might be worth setting glitch rad to 0. And as it recommends here, it's also worth reducing these vel I gate and position I gates down to around 300. They default to 500, which would give an overall better result. Those parameters go together. All right, so that's basically answered Stuart's question. He would probably get much smoother results. He'd probably be happier with it if he just set that parameter to 0, which is a new parameter since when we first started integration of ArduPilot and FlightCoach. Now, Stuart did ask me, he sent me a message last night on Facebook, see if I can find it, somewhere here. He sent me a message where he had some additional questions. So, how to address the bobbles that prompted this. So I think we've addressed that, all right? Sometimes FlightCoach gets the position of flight controller wrong, usually too close to the pilot. The entire flight gets shifted 50 meters left or right. Is there a way to avoid this? I'd need an example of that, and this may well be, is probably an EKF origin issue. But I would need Stuart to provide an example log showing that for me to try to work it out. And it may well be an issue within how FlightCoach is displaying things as well. It can also be what's called registration issues with the satellite view you're using. There can actually be significant errors in like Google Maps, even tens of meters. It's rare these days, but it can happen. So there can be a number of different causes of that. So I can't really answer that one, sorry, Stuart, in great detail. You've got these front, back, and left, right adjustments in the plotter. Shouldn't they default to 0? That's more a question for Arta or Thomas or someone else, not for me. One more about missing messages, EKF. Is it really the memory card or is it a hardware as well? Okay, let's answer that one for him because I might be able to answer that. So what I can is graph dsf.drop. So DSF is the weirdly named message which shows the health of the logging of messages onto the SD card. And this is how many messages are dropped. Because strangely enough, when a message is not logged to the SD card, ArduPilot knows that it's not logged. It can tell, right? And so it logs how many messages it hasn't logged, which is sort of a little bit recursive there, but that's the way it works. And you can see that it's a flat line, right? If this was climbing all the time throughout the flight, then that means that you've got a problem, right? You're missing a lot of messages. But no, he lost 28 messages, and those 28 messages were lost before the log started, right? So this was a startup logging issue where there was a few messages lost. And probably the newer versions of ArduPilot will fix that. We have fixed a couple of startup message log losses in recent versions of ArduPilot. So this version of ArduPilot Stuart has is about a year out of date. It would be a little bit better with the newer one, but it's unlikely that those 28 messages mattered, right? Because there's a lot of messages. If we see how many messages, we can, see how many blocks and bytes and things. So how many blocks total, and this is how many blocks per second. So we're doing like 800 or really nearly 900, blocks per second. And he's lost 28 before the start of the flight. We can also, if you are getting lost messages, you can actually look at the statistics of where those messages are going. So this tells us how much for each of the messages, what percentage of the log was being used. Now, Stuart has both EKF2 and EKF3 enabled, which means that it's doubling up. But I can answer definitively for Stuart, your SD card is fine. It's coping, no problem at all. You don't have an issue with the rate of the logging. There's another trick I should mention, and there's a parameter, which I'm not sure if this parameter was around when we were first doing stuff together, Andy, but you can set this log file rate max. And it looks like Stuart has set it, set down to 30. So don't log more than 30 messages a second, right? And you could drop that reasonably to 15 or so for aerobatics. And that will greatly reduce the amount of data having to be written to the SD card. And so basically I can say that for Stuart's SD card, it was barely ticking over, right? And really not having a problem at all. All right, so now we're sort of well over an hour into it, and we haven't even started on Philippe's log yet. So let's have a look at Philippe. So this was Philippe's, and you can see that it's going to be a different answer for Philippe, right? Because he's got some very creative maneuvering here. So let's start off doing the map, GPS, and pos again, right? And I think I did it the other way around before, pos and GPS. So, but you can see there's some quite large discrepancies. So let's bring up that innovation graph. And so we want EK3 innovation, position innovation northeast, right? So we are getting innovations here of 130 meters, right? Now, you're almost in the wrong paddock. At that point, you're not even within cooey, and you can see this sort of reset behavior. Okay, so because we've been going on for so long, and we're probably down to an audience of like 2 people at this point, Andy, because everyone else has got bored and gone off to go flying. I'll try to go a bit more quickly. Let's jump in and have a look at the compass.
I'm not sure, Trish. I think everyone's still going to be glued to this screen.
You reckon?
Fascinating stuff. Yeah, absolutely.
Oh, right. Well, good to hear that. Yeah, for all those, thanks for sticking with it up to this point. Okay. Now, this is the compass compare predicted graph that we went in earlier for Stewart's, but this one is for Philippe. And there's something really dramatic going on here. This is just before takeoff. And what I'm going to do is graph GPS.speed. All right. And this is the point where he threw on some throttle and started moving. And what do you see happens to his compass readings, right? Now, remember that the Earth's magnetic field is sort of 300-400. I could look it up for his location, on the planet, but it sort of doesn't matter. It'll be 300 or 400 milligauss. And we're getting readings on a single axis down here of like 1200. So assuming he was flying on Earth, then there's something wrong with these readings, right? Because our planet doesn't have magnetic fields that strong in the skies. It does, of course, if you've got a rare earth magnet nearby, or an electromagnet, which is what is happening with the current and the motors. They're little electromagnets. So I can confidently say that Philippe has a problem with the positioning of his compass relative to some current carrying wires that are related to his throttle. Okay, now let's have a look at what sort of compass he's got. His compass is a HMC 5883. He's also got an MPU 6000, which let's go and have a look. Lots of errors being thrown up. His ArduPilot 431, so pretty ancient. I'm not sure when we released that, but might have been last century. It's an probably this century, but just. Omnibus F4 Pro. Actually saying, well, it's a popular board, isn't it? Again, sort of cheap and cheerful. So the same MPU 6000. Now, this compass will be an external compass. We've got parameters that tell you. So yes, it is external. The first compass is external, only got one compass. So this is external. So he's got this extra little HMC 5883 that is probably part of the GPS. Most of these come integrated with a GPS compass, right? And the problem is that where that's placed in the aircraft is far too close to some compass carrying wires. And so the first thing that Philippe has to fix is moving either the wires or the compass. maybe not all that far, though this degree of error, maybe he wants another 10 or 15 centimeters or something. But he really has to move it. Otherwise, he's never going to get a good compass. He would be better disabling the compass than using it, right? And in fact, that's likely what the EKF did. We can actually have a look at the what's called the normalized innovations, and we can see that at least for this part of the flight, this yellow line here is the scaled magnetic field innovations. And when that's above 1, the EKF is just rejecting the compass completely, saying that's clearly nonsense, right? I'm not going to use that at all. But you'll notice that it dropped below 1 in here. And so the EKF thought, oh, maybe the compass knows what it's talking about at the moment. I might start using that. And then what you can see is these SV is velocity, that's the red line, SP is position. These are starting to get spectacularly bad, right? So the EKF made a mistake. It shouldn't have trusted that compass. It should have just said, no, I'm not going to use that ever again. We don't have a compass. I've never heard of compasses. Just trust the GPS and the IMU. And it probably would have been a better flight, right? You can do this, by the way, just an aside, you can do something called replay logging, where you actually log enough detail in the log, and you do need a good SD card for this, enough detail in the log that you can replay the flight with different settings. So you could actually replay the flight with the GPS glitch radius set to a different number, replay the flight with the compass disabled, replay with different weightings for the sensors, and say, what would have happened in this flight if I'd had these settings? So that's a thing called log replay. You also need log disarmed. And just search for ArduPilot log replay to find details of that. It uses a lot of data on your SD card, but you can play around with it then and play what if, what if I had done this in this flight? What would the result have been? It might be worth doing that for people if you're doing a really critical flight where you really, really want to produce a good result and you want to get a nice smooth one, and you're going to be bitterly disappointed if when you load it into FlightCoach, there's this big glitch which has ruined your perfect, schedule. If you'd had log replay, you could actually fix it post-flight, rerun it with different settings until you get smooth results with low innovation so they're consistent. And then you can ask it to generate a new log which has those settings, right? And you could then plot that in FlightCoach. So that's doable. But anyway, it's very advanced. Better to just fix the problems in the first place. Okay, so the primary thing that Philippe needs to do is Philippe Serda, yeah. You need to do is to fix your compass. Let's have a look at his GPS. So sensors, GPS, accuracy. All right. Okay. So now let's zoom in. We got these big spikes at the beginning, right, which were awful. Let's zoom in past those spikes and rescale vertically. Right, you can see that this is the number of satellites growing over here. And this is like 3 or 4 minutes here where the number of satellites is growing. But if we align this graph with the speed graph we've got earlier, you can see that Philippe did do the right thing and he waited for his GPS to be happy before he took off, right? And that means that he had, occasionally down to like 12 satellites, but mostly up to sort of 16, occasionally 18. Let's have a look at, okay, he's got an M8 GPS. Now, an M8 is an older GPS. It's the M10 that Stuart had is a significantly newer GPS. And you'd think that 10's bigger than 8 must be better. Not necessarily. I've actually generally got better results with the M8, M9 than the M10 because the M10 U-Blocks was focusing more on the mobile, lightweight, small, fitting in mobile devices type thing, low power consumption, that sort of thing, rather than focusing on the very best performance. But if you can afford it, an F9P is the gold standard. That's what you should be using, but it's heavy and expensive. But an M8 or an M9 is not a bad choice, and that's probably a significant reason why it actually ramped up to a reason of the satellites more quickly. And you can see the sort of accuracy numbers the GPS was giving. So our horizontal accuracy was sitting mostly around, it's like 1.3 meters, occasionally spiking up to 2 or 3. That's a lot lower than what we were seeing with Stuart. That was a better result. Vertical accuracy, the GPS was much less certain about its height and was sitting, 2.5 meters or so. Speed accuracy, again, reasonable. So the GPS was actually not bad, right? But the compass was so wildly wrong. And the mistake was that the EKF, after initially rejecting the compass, decided to go back and use it again. And that is why Philippe got this, right? It's all about the compass. So, complete rubbish result because he's got a very, very bad compass. So Philippe, what you need to do is move your GPS compass further away from those wires. There's other things, you could again get fancy with multiple GPSs, multiple compasses. Let's have a look at whether he was using the Baro at all. So he was using barometric pressure for height, right? So the vertical position of the GPS wasn't being used at all. And let's have a look at his baro.alt, and we're going to have a look at, again, what the height of his flying fields. It looks like it's height about 56 meters above sea level. GPS dot minus 56. And why are we not getting... Am I... GPS 0.alt and baro.alt. Let's try this again. Oh, maybe he doesn't have... It's not finding a baro. Oh, hang on. This is a really old ArduPilot. Yes. Yes, no, what he's got, param log bitmask. Yes. He's got the log bitmask turned down, so it's not logging the barometer. So it's using the barometer, but it's not logging it, right? And so we can't actually bring up that graph because the barometer is just not logged at all. Now, I would recommend that people actually leave this at its standard setting, and what they should do instead is set that parameter. Now, that parameter log file rate max, he could set to like 20 or 30, which will prevent the problem with filling up the SD card too quickly. But it'll log everything, log all the data just at a lower rate. Let's see if he's getting problems with his micro SD card. He lost 18 messages at startup and then none after that. So he's not having a problem with writing to the SD card at all. But I would recommend he log a lot more things. Definitely log all the sensors you're using. We can, by proxy, get the barometer because we should be able to graph the vertical innovations. That's what's called position innovation down, right? So this is the difference between the estimated height and the observed height. The observed height is the barometer, right? Now, we don't have the raw barometric measures, but we can sort of imply what it must have been. And you can see that we were getting some massive discrepancies up to sort of nearly 15 meters here, right? 14.4 meters there. So that means the baro and the estimate. Now, part of that could have been the compass, meaning that the estimate was wrong, but part of it could be, let's see if that IPD correlates at all with the speed of the aircraft. So what I'm going to need to do is I need the 3D speed. So what I'm doing is ye olde Pythagoras type thing. So is there a correlation between these innovations and high speed? Yeah, not really. There could be with side slip. Potentially you can get the effects where the air coming in from the side affects the barrow. But the interesting thing is Philippe's GPS is actually a lot happier than Stuart's, but Philippe had his GPS height disabled using barometer. So it would have been better the other way around. Probably he would have been better using GPS height. But again, GPS height, a really good GPS would do even better for height. So on my own aircraft, when I'm getting ArduPilot to actually fly the aircraft, I tend not to use GPS as the height estimate unless I've got an F9P GPS or a UM982 or similar high quality GPS. Just because the height estimate, you really don't want to land underground. And landing too high is bad as well. Then it flares and it finds, expecting to settle down on the ground. And where's the ground? Where's the ground? Stall, bump. So bad result. Okay. All right. So I think the message for Philippe is compass, compass, compass. Move that away from your current carrying wires. The EK3, I don't think. Oh, we did have glitchrad. So this early version of ArduPilot did have the glitchrad parameter, but I'm pretty sure the glitchrad parameter didn't have the special case for 0 in that version. For that, you want recent ArduPilot, like 4.6 or 4.5 has it, but 4.6 would be the preferred. So 4.6.2 is the current stable release as of today. So you'd install 4.6.2 firmware and set that to 0 if you want to completely remove those sort of glitchy things. And fix your sensors. So, all right. We've been going for an hour and 40. You reckon we've still got some audience left. So anything last that you'd like to ask Andy?
Tridge, I think that really covers things really well. I think two things that would just be really useful, and I just very briefly for mounting the flight control, and in fact the GPS as well, is something like Velcro acceptable, or just what would be your quick and easy mounting recommendation for people?
It depends a bit on your flight controller. So these both Philippe and Stuart were using Omnibus F4 Pros, which use these ancient cheap MPU 6000s, which they actually have quite a good gyroscope in them, but less good accelerometers, which means they're more vibration sensitive. We haven't had a look at the vibration in this plane. We haven't logged it because he had the log bit mask turned down, so the vibration isn't even logged. So we don't know how bad the vibration is in this aircraft. Again, leave the logging at default, but just turn down the rate of logging is a much better idea. So I quite like Dubro foam. I've probably got some here somewhere. This sort of stuff, that sort of thing. Although for a lot of my aircraft, I've got an internal combustion engine in there, like a petrol engine, and so it matters more with the big thump, thump, thump of the petrol, exploding. There's less explosions going on with electric aircraft, hopefully. Yep. Not always. But this sort of stuff is very good. But for most people, the vibration isolation, it will help, but not by a massive amount. The alignment of the flight controller, that's quite important. Make sure it is actually pointing straight forward. Right. Or if it's not pointing straight forward, if it's like 90 degrees off, you set the parameter so it knows that it's 90 degrees off. I often mount just with Velcro, but I'm also using more modern flight controllers, like this sort of thing, or all sorts of others. Where have I got another? Anyway, more modern ones which have much better IMUs, and are sampling at a much higher rate, and are less vibration sensitive. So these old ones, like the Omnibus, the F4 Pro is more sensitive to vibration. So one of the things I used to do, particularly on internal combustion planes, is like a aluminium plate, then a layer of cubes of that sort of foam on the corners of aluminium plate, and then like a little bit of ply, and then the flight controller on Velcro. And that way it's actually on a layered of this foam, and there's only little cubes of foam at the corner of this plate. The other thing that can happen is vibration coming in via the wires. That's not uncommon to get a wiring problem. But don't spend an enormous amount of time on vibration isolation, because you're far more likely to get problems with your compass than you are with the vibration isolation. And the other thing is get a high quality GPS. And particularly if you can get a dual frequency GPS, that can make a very big difference. Did you do some experiments, Andy, with two GPSs, one pointing up, one pointing down for
I did,
aerobatics?
yes.
Yeah,
Yeah, yeah.
what was the conclusion from that?
It didn't find it made a huge difference. Made a small difference, but not a huge difference.
And you were using blending between the two?
Yes, that's right.
Yeah,
Yeah.
so you can set them up as blending. Yeah, so it's probably that I think you already had pretty darn good results to begin with.
Mm.
And you were getting, my vague memories of maybe M9 GPSs you might have been
Oh,
using, something like that. Yeah,
yes.
which are good. They're the M9 will be better than either of the two GPSs we've looked at today from Stuart and Philippe. Um, uh, so that's probably why you didn't see as much of a difference. Um, and Yeah, but if you really wanted to mean that little tiny F9P that I showed, marvelous GPS. I don't know how much that's selling for. Let me go and have a look. Um, uh, uh, that's might have been, yeah. So 325 US dollars, right? It's not cheap. And there's some shipping issues from China at the moment. You may not even be able to get them easily. But then it's nice and light. It's a nice integrated compass, lovely helical antenna built in. It is a lovely GPS. Um, the but expensive, right? And luckily with the L5 frequency coming online, and there's a funny thing about GPSs that are like L1, L5, so they've got two bands. The L5 is not currently used by default because it's still marked in the satellites as being under test, but you can override that in ArduPilot. Tell ArduPilot to force the GPS to use the L5 even though it's not marked. And given there's not like a safety of life issue here, I would be, if I had an L1, L5 in an aerobatic aircraft, I would be enabling the L5 because L5 is a better frequency. It's got a better modulation. It can pick weaker signals out. So there are some new L1, L5 U-Blocks GPSs that have come out that are worth having a look at. And they're going to become more common. Once L5 goes full production, I expect that the cost of dual frequency L1, L5 GPSs is going to come down fairly quickly. And they're going to be a really good option. And the results for people using FlightCoach are going to get spectacularly better because it'll tenaciously
Exciting.
hold a signal when inverted and things. You get a lot lower innovations. So that's something to look forward to. You can jump into that world now if you want to, if you've got the money. But I'm expecting that this will become normal in the future. And everyone's going to end up with much more accurate equipment. Yep. All right. So I might stop screen sharing, and we're just about done, I think. So thank you all for listening. If you've managed to get through all this time, it'll take me a while to upload this video. And feel free to, I'll post it in the Flight Coach group on Facebook. And then, hope you've all sat down with your popcorn or coffee or whatever and watched through. And hopefully something useful will come out of it. And yes, I will look forward to seeing the results. So thanks very much, Andy. And I'll probably stop the recording there. Thank you.